All right, so good morning. So the good news is that I'm really your last talk before lunch. The bad news is that I intend to take really the 24 minutes that I have before the 1 p.m. time clock. So seriously, we are having a good time here, and I'm sure that most of you won't trade your position for, well, the black screen for that one. And you may see that young fellow here, and you may see on his face, maybe he has some concerns, maybe he doesn't, but I do have concerns. And my concerns are that I have absolutely no idea of what his sound exposure will be here in that aircraft. And we had an excellent aircrew presentation yesterday, and in the battlefield. And when I mean exposure, I don't care about the sound pressure level in the aircraft. I don't care about the dosimetry, at the shoulder level. What I care for is really what's reaching the eardrum. So that's really my quest. And that has been actually something that people have been looking for in the industry for a while. So we heard this morning that there were military products just about to be released from our friends from Embedded Acoustics. But if you look in the civilian industry, this is something that was there out around 2009, and that was, I guess, the very first in-ear dose measurement system. Very simple, very, very brutal, I would say. A microphone and just an SPL LEQ accumulator. So that was the quiet dose. And if you look in the days, you had as well some more of the metrological companies that were interested in in-ear noise dose. And here's a Svantech device. I was part of partnership with a company that made actually a product that was intended to feature and to monitor that in-ear dose. So the company is out of Montreal. But eventually the product that we co-developed was bought and adapted later on by 3M. And last time I checked, I just had a small talk this morning, the in-ear noise dose is not something that we'll see, that soon on such devices. But fortunately, we have some other colleagues and friends, thinking of Olav Kvalov in Norway, that have been really commercializing those in-ear products. So not only hearing protection, but really the dose measurement from inside the ear canal. Nevertheless, if you've been here 2 years ago, you may remember that there were some outstanding issues. And the outstanding issues is really that when you measure inside the ear, you have to account for a lot of corrections. You have to maybe calibrate on an individual basis. You have maybe to account for noises that are produced by the wearer itself. So if I'm coughing here, that may be super loud in my ear, in my ear canal. Is that really dangerous for my, exposure? Does that count? This is a research question. Nobody has clearly the answer. So we need to have maybe the ability to account for wearer-induced disturbances as well as outside noise in different budgets. And we need to be able to measure in loud, impulsive noise as we do have in the military workplace. So the first three topics are actually addressed, and that's another plug in that working group that we are just starting with Kevin Michael under the auspice of the American National Standard Institute. We have a year still to develop what we called recommendation for in-ear noise level monitoring devices. And we will actually have a working group meeting tomorrow in this very place, Thursday afternoon at 2:30. Several of you are already registered for that event, but still, I'm just mentioning that we already have a scope, a title, and a little bit of an approach. And then tomorrow, hopefully, we'll do some task force on that. But today's talk is really about the instrumentation. How can we measure inside the ear some very high levels? And so if you're not familiar with an in-ear system or in-ear product, I'll be just sharing with you very openly the type of product that we developed and that is used for research purposes. I'm an academic, but that our partner company put on the market as well. So basically you have that dual element, that's a loudspeaker, bass and treble, and then you see the little microphone that will be inside the ear. So typically we have them, in a sort of isolating plastic. We typically have an external microphone, so you see here that microphone, and a PCB, so a connection. And when we have that earpiece interconnected, you have really what we call the instrumented earpiece. And you can add on the back an ear loop or ear hook where you put some electronics. So you can have a DSP, you can have some processing power. We can as well have wire connection, and this is what we use a lot for research purposes, not necessarily for product. And at the end, you can fit on top of that an earpiece. It can be a custom earpiece. That was the case for the Sonomax earpiece that you see here in orange. That can be a foam tip, that can be anything you want. But I wanted to really show you what was inside, because that's really what matters here, is that inside that earpiece, you have again that microphone and that dual element speaker. And how am I going to measure the in-ear noise dose? Well, the first idea is to say, well, let's use the in-ear microphone. But the risk is that it will be very quickly clipping. If this is too loud inside the ear canal, you know that most electret microphone, most technology that we have in miniature size will be clipping at levels like ranging from 120 to 140 peaks. And so quickly you have that limitation. So what about damping that microphone? So that's the first idea. Could we simply have that microphone and have some kind of damping? So here the original idea was, can we add fluid? So think of water, that would be just doing an interface. So you move the air, the sound wave will move from the air to water, then to air, then to the microphone. And you do have serious attenuation because of the phase change, transition between the various fluids. And putting that into a test, the idea is that we took that little microphone that you've seen and we'll basically mount that into a tube, over a tube, and inside that tube we'll have the ferrofluid that would be held actually with magnet. So that's our trick, to get that little drop of water, if you want, to be stable and not to leak to the eardrum. So that was our first idea, damping a microphone. And then we had a second idea. We said, well, in acoustics, you do have that reciprocity principle. You remember that something that you send energy to produce sound, so typically a receiver, a speaker, can actually be used as a microphone. If you have a sound wave that is reaching that speaker, it can generate some electricity, some voltage actually, and that was the idea that we wanted to explore. Can we simply have a switching circuit that make it so that the speaker that you have on the right side here, which is usually playing back all these controlled environments that are required for the soldier or worker, can we use that speaker as a microphone? So we will need to switch. Each time we detect that there is a blast, and it's the blast detector, we would switch that speaker to a microphone element. And so that's the second idea that we tested in the lab. So actually it's not a very new idea, and this is a project that I shared a little bit earlier. That's something I did, I think, more than 10 years ago with the Israeli Defense Forces. They were having issues with their NCB face mask, because if I'm wearing something in front of the mouth, right, it's super hard to guide people for NCB process. And so we had that in-ear microphone that was picking up the speech and the voice of the person, the military person, except that that was a two-way communication system. So we could speak and listen through that one receiver inside the ear through a push-to-talk button that you see on the PTT lower left. So it's not really new, but let's try that. So the first campaign was done in an anechoic room, and we tested both what we call the IEM. So IEM, that's the in-ear microphone, and the speaker approach that I mentioned, meaning that we use the speaker as a microphone. So the setup is here we have obviously the calibration step, and here are the various microphones that we tested. So in yellow, you see the yellow cycle, that's a high dynamic electret microphone that has a very special power supply to get the extra headroom. So this is really what the best hearing aid microphone can do. On the right cycle, you have the reference microphone, so you see a high dynamic pressure mic from Grass. And in blue, this is really our little tube with that drop of ferrofluid and the microphone damped by that system. So now if I just look at the sound source, that was a civilian experiment. So this is my hammer and just an aluminum bar, and it does a very nice ringing noise, as you can imagine. And you can imagine that from the ringing noise here that you see the pressure in Pascal, so that's not really huge. But probably something you would have in the industry. And now if you really look at what this microphone records, this is what you get with this damped microphone. So that's something that looks quite similar. That's the original waveform. And if I now look at what I'm recording on the reference microphone. So again, the reference microphone is this grass microphone. And if I look at the peak values, you see I'm just reaching 120. That's not huge. But if I look at the damp microphone, here there is no calibration, but you see that I recognize some of the waveform, but with a huge damping factor. So that was, I would say half conclusive. There is hope, but when you look now at the transfer function, so between that open tube condition and the sealed tube, you can see the very good attenuation that we had with the solid tube. You can see the effect of the oil film. You can see the oil drop. So there are various things to be used, and we could correct the response from that. But what was interesting is to look really at the speaker response. So again, on the left, that's the good grass microphone, and on the right, that's the response from the speaker used as a microphone. So you can see that there is something that clearly looks like it's recording properly those peaks that you have on the top of the screen. So if I do now just a simple calibration, so really accounting for the transfer function I've shown you, you can see how I can recreate the original signal with that speaker recording inside the ear. And here again with the peak values that are not exactly there, but not too far in terms of envelope of the peak values again. So if I look at the distribution of those values, peak values from the reference mic, so the grass, versus the speaker predicted values, you see actually that there is quite a good alignment. So around 135 dB peak, you see that the values are nicely aligning. The predicted values are very close to the reference values. And you see that there's maybe a little discrepancies at lower levels. But remember, at lower levels, we have the IEM, the in-ear microphone, that works just normally. So we could combine actually in-ear microphone and the speaker as a microphone to get the best of both worlds. And if I look at the distribution of the error, so residues are distributing normally here, which is a good news. It means that we could just express uncertainty on those measurements done by the speaker. So let's dig further into the speaker, the use of the speaker, and 12 minutes ahead. We can now do the measurements in a reverberant room. So that was just to get a different sound field. And you see here the horn that we'll be using. That is actually reproducing the blast of a gunshot, and that will be used on an ATF. And so you see here the ATF being equipped with the earpiece and with the reference microphone outside. So that gives us a couple microphones, quite a few microphones. So there are first what's outside. So outside you have the reference microphone, you have the inside you have the in-ear microphone and the ATF, artificial test feature microphone. And if I look on the schematic part of things, so you really have outside the reference microphone and the other microphone, and inside you do have again the in-ear microphone, the speaker, and the ATF microphone. So that's really 5 channels that we're gonna record, and we're gonna simply record them in the time domain with again that sound from a shotgun that was recorded and played back with that choke tube. So calibration obviously of the reference mic and the ATF. We don't calibrate anything else. We just do cross comparison. And so reference is here and ATF is there. And if I look at the reference signal, that's the peak. Those are the 2 explosions that we recorded on 5 seconds. And the ATF records quite similar, signals. If you look at the outside microphone is actually clipped. I don't know if you can realize that, but the signal is too loud, so you don't have the proper time envelope. And the in-ear microphone gives you something a little bit odd. You may see that there is some, timing issues, and there will be some clipping. We'll see that in a minute. But if we look at the speaker recording, you see that it's a clear signal that is in proper dynamic range, and that we're gonna further study. So if I'm just plotting again the peak values, you get so that was now reaching 150 dB, so closer to very small weapon or small caliber. And then the ATF gives you obviously the attenuation of the earpiece, so you can see that we had a decent attenuation from the earplug, instrumented earplug. And if you look at the OEM, now this is super clear that the OEM was saturated. And the IEM, as you can see as well, didn't record any peak because it was clipping as well. And for the speaker, you see here, this is uncalibrated, but we have a clear peak values and a shape that looks a little bit like the reference microphone. So obviously, if we compare the reference and the speaker now, and we really look at those shapes and envelope, well, they reach the same peak values, which is cool, but they don't really have the same temporal content. And if we care about the envelope of that impulse noise, obviously we miss some information. So that's probably frequency dependent. And indeed, if we look at the transfer function, so in the frequency domain on the x-axis and on the y-axis, that's the magnitude of the transfer function, we see that the speaker does not measure exactly like the microphone of the ATF, of the head. There is a difference, and you can see that difference if I'm in open condition, that's the red line or orange line, so you see clearly the ear canal resonance effects and a slow rolling down effect. And now if I'm just measuring inside the ATF, the transfer function between the speaker used as a microphone and the microphone of the head, you see that we have some other resonances. And firstly, that's explained a lot by the fact that the coherence in the transfer function, that's the quality of the measurement. Well, we can only really trust the measurement that we did in open fit, so the correction between the speaker used as a microphone and the ATF microphone will be that orange curve, because that's the the orange correction, open correction, because this is where we get the best coherence. So now let's apply that transfer function to the measured spectrum and temporal impulse, and this is what we get after the correction. So you see that we still keep our peak values very close, and we recover the proper size and shape of the temporal envelope of that blast. So I think that's a little bit of the the proof of concept that we wanted to run here. There is obviously so it's orange because we still have work to do. I'll go back to that in a minute. But this is definitely giving us a possible approach to measuring in-ear levels. So I think that in conclusions, we could use a liquid damped microphone. They have benefits over membranes, over mesh, over a lot of elements that would introduce non-linearities, and I think ASL is very well known for the non-linear earplug, so liquid has some benefits. But the fact that there is always, or most of the time, in-ear receivers, speakers, and that they can be used as a low sensitivity microphone, I think is actually a treat. We can use that. And the fact that we can simply use the transfer function measured in open ear condition is actually nice to know. And the need for that switching circuit, so that we can use the speaker to play back all the ambient noise and communication signals and so on. But at the same time, as soon as we need switch that back to a microphone, is something that is really adding value to this proposal. So there is more required. So the dynamic range of those excitations is quite limited. I'd like to have values that are from 80 to 100 dB, 150 dB in ear levels, and on a broader range of sources, so not just that gunshot, but various types of noises. And there is as well a challenge. So here there is a lot of real-time DSP people in that room, and you can realize that there is a challenge in the fact that for me to detect that there was actually a blast coming in, this is already too late. The blast already reached the in-ear level, and I didn't switch my microphone or my speaker to a microphone position. So you need to work actually with a lot of buffering and first in, first out buffer, so FIFO. And this is what we actually just filed in a recent patent application, to have that option to really post-process each peak as it reaches the what we call the black blast detection block. So nevertheless, we are open for collaboration. There is more work required, especially for the wide range of sources, and so we are always interested for more people joining the efforts. And on that note, here's my contact information.